Now, let's consider this example. A force of magnitude F, constant magnitude equals 5, is applied over a period of time that's equal 1 second. After that, the force applied is 0, and I'm going to try to find the response of the system as a function of time due to this input. First, the system given as x double dot plus 10x dot plus 169 x is equal to f of t, and I can obviously determine that the frequency, the natural frequency omega n is 13 radians per second. Omega d can be determined to be 12 radians per second. Zeta is 5 divided by 13. This can be determined from the characteristic equation of the system. Now, I know the step input response, the unit step input response x of t was the input response f0 divided by k times 1 minus e to the power negative zeta omega n t minus t0 times cosine omega d t minus t0 plus zeta divided by 1 minus zeta squared sine omega d t minus t0, and closing this bracket right here. This is the general step input response. In my case here, F0 is the magnitude of the applied step, which is 5. So F0 is 5. But now what we have here is not actually step function. We can consider this as a combination of two step functions. We can split this as follows. First, I will have a step function of magnitude 5 applied starting from time t equals 0, but this goes on to infinity. So I will add another step of magnitude negative 5 at time 1. Now if you add these two steps together, you will get this total step. 5 plus 0 until we reach the 1 second point becomes 5 minus 5 is 0. So the total of these two steps is the step or the input function that we have, the constant input over a period of time 1 second. So now let me determine the response due to the first step. The first step exists alone between 0 and 1 second. The second step does not apply until we reach the 1 second marker. So for time t less than 1 second, I only have one input which is 5. So x of t is going to be 5 divided by 169. 1 minus e to the power zeta omega n is going to be 5, -5, and t0 is 0. Step 5 applies at time t0 is 0. That's the beginning of the step function here. So this is going to be -5t times cosine omega d is 12 t minus t0 is t plus zeta divided by 1 minus zeta squared is 5 divided by 12 sine omega d, which is 12 t, and that's my response x of t in the region between 0 and 1 second. So if I plot this over here, it's a damped response. It's gonna look something like if I continue to plot this function after t 1 second, it'll continue until it reaches a steady state. Okay. Now, but this solution applies only to the period from 0 to 1. So now, what happens for the solution after 1 second? After 1 second, I will have to include both steps. So I will have the response due to the first step, so for t greater than 1, for both steps. For step number 1, I have this response, x1. Now, x of t is going to be x1 of t, I call this x2. So x1 of t minus or plus the -5 force, -5 step function, plus -5 divided by 169 e to the power -5 t minus, now t0 is 1, times cosine omega d is 12 t minus 1 plus 5 divided by 12 sine 12 t minus 1, and that's the total response. And now if you plot this function starting at t equals 1, you will see that the response will drop to 0. So this alone, this is x1, and right here x2, which is the total of the response of the first step and the second step. So I will only consider x1 from the period 0 to 1 second, and then after that this response is no longer valid. The total of those two steps, so the response of the total of the two steps is the response that I'm going to consider. So this is my total response to an input of this form. So basically any square input can be split into a sequence of unit steps or step functions. For example, let's consider if I have a function that doesn't start at 0 but starts at some time and then drops like this. If this is f of t, let's say this is 4 and this is 2, 1, 3, 5. To generate this profile, I will have to add first a step of magnitude 4 at time t1. Then to drop down 2 steps at 3 seconds, I will add a negative step of magnitude negative 2. So now if you add these together, 4 minus 2, that will take you to 2. And that continues until 5 seconds. That's when I apply my second negative 2 step. And if you add this negative 2 step, 4 minus 2 minus 2, that will take you down to 0. So you can split any step input, regardless of the number of steps and the sizes of the steps, into a sequence of steps and find the response to each step separately and apply that response according to the distribution of the steps. So the response to step 1 applies only, for the time 1 to 3. From time 1 to 5, I will have to include step 1 and step 2. And after 5, from 1 to t, all the steps are included in the response. And I will follow the same procedure here, determine the step response of each input separately and then add them up. And the most important thing is to specify exactly and very clearly which response belongs to which time domain. This response applies only from 0 to 1 second. This applies from 1 to infinity. So you have to specify this very clearly.